In the previous lecture, we introduced the basic concepts of probability. In this lecture and in the next lecture on simulation, we will be talking more about modeling and dealing with combinations of events where the business situation or the personal situation that we're dealing with is more subtle, is more complex. We'll build upon the basic building blocks of probability that we developed earlier, but now we want to try to deal with some subtlety that will enable us to build some more sophisticated models to be able to get our hands around a more complex business situation. As I've mentioned throughout this series of lectures, the business reality or the world in general is quite complex, and the extent to which we can build a model which is manageable and yet enables us to deal with some of the subtlety is the extent to which we build good models and are doing good data analysis. As an overview for this lecture, I'm going to start by providing an introduction to simulation, as to what simulation is about, and specifically I'll talk about a new product launch decision. I then want to go over and review the concept of a Venn diagram to be sure that the spatial representation of probabilities that Venn diagrams afford is familiar to you. I want to talk also about conditional probability, independent events, and finally, I'm going to give you a problem at the end of this lecture. Now, since you're not able to respond to me directly, I will work the problem. I will not, as we say, cold call on anybody in the audience to work this problem. I don't want to get the audience nervous at this point in time. I will work the problem, but I want to check your understanding to see if we're connecting. Let me say a word about simulation, first of all. I'm going to detail this in a much more at a much deeper level in the next lecture, where we go into it singularly. But for now, let me provide you with an overview of what is called Monte Carlo simulation. The Monte Carlo simulation goes back to the 1940s, actually, where the possible effects of developing the atomic bomb were simulated through random processes. But it turns out that Monte Carlo simulation is now used quite extensively in business to deal with probabilities and uncertainties in business situations. And the situation we'll look at particularly is a new product launch. There are 3 steps to Monte Carlo simulation, and there are many popular software packages that enable this to occur inside of a spreadsheet, which is, it turns out, one of the more common ways in which business today uses Monte Carlo simulation. The first thing that you will do when you build a Monte Carlo simulation is generate what are called assumption cells. And I'll give you an illustration of this in just a minute. Then what you will do is you will, given those assumptions, calculate the values inside of a spreadsheet, let's say, maybe 100 times, maybe 1,000 times. And as it were, what's occurring, and I will try to make this more plain as we go through, the new product is taking on 100 possible lives. That each calculation of the spreadsheet generates, say, for example, the cash flow associated or the revenues with that new product. And what you're doing is you're developing a tracking mechanism for the range of possible revenues given your assumptions. And we'll illustrate this in more detail as we go forward. So the third step is to actually display your results inside of a forecast chart. So you're going to see the range, not only the range, but the probabilities associated with each revenue number or each cash flow number, whatever it is that you want to display. And Monte Carlo simulation is one means of getting your hands around the range of possible values associated with a product or series of products. One of the things I did once was to do some Monte Carlo simulation associated with a slate of films that a Hollywood studio was producing. The question here was, one film is very risky. It can have a very broad spread as far as revenues is concerned. It either can be a breakout, a bust, or it can perform in the middle range of domestic theatrical revenue. And then, of course, we also have to think about foreign theatrical revenues. And there's other revenue lines which must be dealt with, like video rentals and pay-per-view. And as you can imagine, the models get complicated, but that's not my point now. My point is that what we wanted to do was to develop some way of simulating the movie studio's performance in domestic theatrical revenues for the next year. And what we did is that we enabled the studio, as it were, to live 1,000 lives. In essence, what would happen if we reran this studio's next year's event 1,000 times, or 10,000 times? And we get 10,000 possible revenue values for the slate of films in aggregate. And then I can see how those are distributed, and then we can get some sense of confidence as to where the range of values might lie. Now, let's illustrate this in some detail. Let's talk about a revenue forecast model. And in the revenue forecast model, you'll notice that we're simulating a product launch. Now, here are my assumptions. The first assumption is, what will I be able to charge if I have no competitor enter my market? And here I have revenues for 1997 in the model. Notice that in that price, no competitor cell, right now is $70 per unit that I can charge for my product. However, sitting behind that 70 is an assumption. And the assumption that sits behind that may look like the following. Maybe $70 is my most likely price, but I may also have a minimum and a optimistic price. For example, maybe my minimum is 60 and my optimistic is 90, let's say. And the height of each value is related to the probability that I'll be able to charge that number. So it's most likely that I will charge 70. But, and it's very unlikely, but I could charge as low as 60 or I could charge as high as 90. So picture the following. Here I have a spreadsheet cell 70. But sitting behind that cell is the mechanism to each time I calculate the spreadsheet to be able to pick a value in this range. And the likelihood of a value being picked is proportional to how high the triangle is at that value. So at $62, it's relatively unlikely. At $70, it's much more likely. Now, the type of assumption I put in behind this model is very flexible. Here I have built what is called in the parlance a triangular distribution, because it looks like a triangle. Its shape is triangular. I could put, as we'll talk later, about a normal distribution. I could put a Poisson distribution. There's all different ways in which I could describe the likelihood of any particular number occurring in this model. By the way, business people tend to like triangular distributions for simplicity reasons, because a lot of times they think pessimistic, most likely optimistic. Since business people think this way, sometimes they'll model with a triangular type of distribution. But this is one of the assumptions that will come into my model. What revenue will I be able to sustain in the marketplace given no competitor? Notice in the model also there is price with a competitor. Now, this 70 number just happens for this one time to return the most likely value. Every time that I would recalculate this spreadsheet, another number would come in here which would be driven by this distribution. Now, price with a competitor here is 50, but that might be another assumption cell. So I would have another distribution which might look like this. I might have a distribution with, I'll make another triangular distribution. Maybe the price, if a competitor enters, is tighter, 50, 40, and 60. So this would be an example of a distribution which would drive this cell. I'm going to recalculate these 1,000 times, and I'm going to track my key output variable, my forecast. And what I'm forecasting here is sales revenue for this new product, sales revenue. Now notice, I'm not done yet with this rather basic model, but let me give you one other dimension. And that is a competitor going to enter or not? See, these here are continuous in the sense that any value could be assumed for the price if the competitor doesn't enter or the competitor does enter. But the competitor entry, notice, is a 0 or a 1. So up here, and I'll put it at the top for space, I don't know whether or not my competitor is going to enter. And right now it stands at 0. But the assumption that stands behind that variable might look like this. Maybe it takes on a 0 or a 1, a discrete distribution. A 0 means no entry, and a 1 means yes, they do enter. So what happens here is, and maybe these are 50-50. Maybe it's a coin toss as to whether or not my competitor is going to enter. If my competitor doesn't enter, I can charge this higher price, and that's what's going to come down in my model under sales price. If a competitor does enter, the value that the computer generates here randomly from this distribution will come into my price. And similarly, my volume might be uncertain. I might also model my volume, my sales volume. So I really am not sure exactly what it will be as a point, but I may be somewhat comfortable in describing it as a range. And not just a range. The difference here between just saying that it could be in this range and simulation is that I'm not only stipulating what the range could be, but I am also stipulating the probability associated with each value in that range. And we'll talk more about this when we discuss the notion of simulation in more detail. Right now, if you don't understand exactly everything I'm saying, don't worry about it, because we're going to be discussing simulation next lecture in more detail, and I'll fine-tune it somewhat. Right now, I just want to introduce the notion of simulation. So what happens now is that I come down to my forecast number, which is revenue. And right now it stands at 385,000. Each time I run this model, it's going to pick a number. It may be that the competitor doesn't enter, and I can charge $80. The computer is going to do this for me. It's going to randomly generate possibilities based on this distribution. So I charge $80, and I have volume of, maybe I come up with 5,000 units. So it's going to give me 1 point, and that point in this case will be $400,000 in revenue. It's going to track that point. It's going to do this Well, I did it in the example here that you have 500 times. And in the example that you have, notice that I have a revenue chart, a forecast chart for 97 revenue, which gives you the likelihood of revenue in a histogram form. And there's 500 trials, which means that I allowed this product to live 500 lives. 500 possibilities based upon the data that I have. Now, obviously, the extent to which I can build a good assumption distribution will enable me to get a tighter forecast. But if I'm not sure about my assumptions, then I may have to put a pretty wide range here in building my simulation model. But the one thing I want you to see at this point in time is that I'm now starting to combine events. I'm starting to use probabilities however I derive them, be it through my database analysis of my market response or whatever I'm doing, or be it through subjective assessment of going to an expert and asking them, what do you think the minimum price we can charge? What do you think is most likely? What do you think is optimistic? I build the assumption, and in then proceeding, I'm able to come up with a revenue forecast which enables me to see a spread. In the forecast chart, you'll notice that there's two humps. It's almost like a double camel hump, and I suppose that relates to whether or not the competitor enters the market or not. And you'll notice that I have also given you a range of values from 146 to 463K. I essentially have chopped off a certain part of the extreme values. Each one of these spikes contributes, each one of these revenue values that I get out of the simulation contributes to the height of one of those spikes. So looking at this forecast chart, it gives me the range of possibilities. It also gives me the likelihood of those possibilities. So simulation enables me to try to get my hands around ranges. Now, if the range is particularly wide, I may want to try to develop a better forecast for my revenue. Let's talk now about Venn diagrams. I'll come back to simulation in the next lecture. I want to explain that in more detail so that you see some of the subtlety. But right now, I've just painted it with a 3-inch paintbrush, a 4-inch paintbrush. We'll come back and do it with the 1-inch paintbrush in the next lecture. Now, the reason we want to spend a little bit of time on Venn diagrams is that you can see how probabilities can be depicted spatially. Let's go back to the diagram here. And here is my sample space. X is everything that can happen. X is everything that could occur. Now, I have an event A. And if point A occurs, if event A occurs, the point will fall inside of the circle. If it doesn't occur, A doesn't happen, and that's everything else. So this is known as a complement. A and not A. A spatially represents the fact that the event occurs, that the event happens. A might be, I'll get my job offer at Netscape if I'm applying to a company. Not A may be that I'll get dinged. I will not get the job offer that I wanted at the company that I'm applying for. And I can represent either, and the whole space is, in this case, related to job offers. Netscape, not Netscape. Okay? The next one here is what we call intersections. Now here I have A and B. I have A and B occurring, and the crossed hashed area says that I will get both A and B. So this means I'll get the job offer at Netscape and the job offer at Microsoft. This area that's in common. Again, not precise mathematically, but just trying to spatially represent what's happening with probabilities. Now, if two events don't overlap at all, if they both can't happen, They're mutually exclusive. We term these mutually exclusive. Now, for various reasons, I've made A very small, as you'll see, and B relatively large. Let me give you an illustration. Let's say that event A is, within the next 30 seconds, we're going to have a major earthquake in Virginia, where we're doing this taping. And event B is that there'll be no earthquakes in Virginia today. Now, those are mutually exclusive. They both can't happen. Now, if I were in California using that example, people might start getting nervous. But I'm in Virginia, so consequently, it may be that we can deal with that question with a little bit more calmness, because the probability of A occurring is very, very slim. In fact, we'll know within the next 10 seconds whether or not it happens. I don't think it's going to happen. Otherwise, we'll have to do this shoot again. But B is, this is an example of disjoint, of mutually exclusive events. And I can now safely conclude that B has occurred, and we have not had any earthquakes, at least I can't say for Virginia as a whole, but where we are in Virginia. Now, one thing about intersections that I want you to notice, because this will be important when we talk about combining events, because whether we're talking about simulation, where we're combining competitor entries with revenue and volume and trying to get some type of combination, simulation enables us to put a series of events together and combine them. Venn diagrams also is talking about combining events. I want you to notice one thing for me, because we'll need to deal with this. And that is that if I want to know the probability of A or B, okay? And let's go back to the Netscape Microsoft. Either I'll get a job at Netscape or Microsoft, a job offer. I just can't add up these probabilities. I just can't do it. If the probability of me getting a job at Microsoft is 0.6 and the probability of Netscape is 0.5, it's clear that I just couldn't add them up, because that would add up to 1.1. And as I told you in the last lecture, probabilities can only be a maximum of 1. Those are the quote-unquote absolute gimme putts, which are a quarter-inch away from the cup. See, if I add these up and they're not mutually exclusive, I have to realize that I'm double counting this area that's in common. So in fact, what I have to do is I can say this is equal to the probability of A plus the probability of B, but I have to subtract off the probability of both of them happening. Both A and B occurring. Because otherwise I'd be counting this crossed area twice. I just want to count it once. I have to count it once, so therefore I subtract off P of A and B to be able to get to the probability of P of A or B. And now, what's the bottom line on Venn diagrams? The bottom line on Venn diagrams is that most people sometimes like to spatially represent probability relationships that involve more than one event. And Venn diagrams are one way to do this, to spatially represent what's occurring when events are combined. Let me talk next about conditional probability. Whenever you revise the probability of an event to reflect information that another event has occurred, you have what is called a conditional probability. Let me give you an illustration. Let's say that the Boston Celtics have a 10% chance of winning when they're beating Chicago Bulls at home. Let's say that the probability of the Celtics beating the Chicago Bulls at home is 0.10. Okay? But if I tell you they're ahead at halftime, you might revise your assessment as to the probability of whether or not they're going to win. And what we do is the following. If I write the probability of A given B, what this means is that, and in the case I illustrated, this would be 0.60. The probability of A might be 0.10. The probability of the Celtics beating the Chicago Bulls at home might be 10%. But the probability of the Celtics beating the Bulls at home, given that they're leading at halftime, that another event has occurred, might jump up to 60%. This is an example of conditional probability. Well, let me give you another example. In fact, let me give you a couple other examples so you get a sense for what's involved in this. Let's say that I were to look over the audience and say, what's the probability of somebody in the audience being able, since we'll stay with basketball for right now, being able to slam dunk a basketball? And I might say the probability is rather slim. It might be 0.02 that someone could actually slam dunk a basketball in the audience. But if I told you that somebody in the audience is 6'4" or taller, and I say, what's the probability of being able to slam dunk given that someone is 6 foot tall, 6'4" or taller, it might go up to 60%. So the fact that I give you one event can dramatically impact the probability of another event occurring. This is what we mean by conditional probability. And oftentimes when we build models, say simulation models, what we want to do is ratchet up or down the probability of one event occurring, or how it's distributed, given another event occurs. And we saw this earlier, that the revenue number, the sales number, the price that I could generate or sustain was dependent upon whether or not the competitor entered my market. If the competitor entered, what I could charge was less. So consequently, the conditional relationship of sales or of price was dependent upon whether or not the competitor entered. That's an example of conditional probability. Let me give you a third example so that you kind of see how this might work. Let's say that you are trying, let's say you have determined that for your company a acceptable product defect rate is 1%. That might be too low or too high given your situation, but you want your product defect rate to be just 1%. And let's say that's event A, that the product defect rate is 1% or less. The probability of A occurring right now might be rather remote, 10%. The chances are that you will not be able to execute production such that your product defect rate is only 10%. But now, let's say that somebody maybe is trying to sell you something, a quality control product or process, or maybe a new product manager. Let's say event B is that you bring in a new product manager who is very, very talented in some way. And she will be able to change the chances that you'll be able to achieve your goal in product defect. In other words, be below 1%. So the probability of A, given that I've hired this superstar product manager, product control process, this may take it up to 70%. So again, I have the probability of one event revised to reflect that something else has occurred. And if I revise the probability of one event to reflect the fact that something else has occurred, I am illustrating conditional probability. Now, let's talk about independent events. Independent events occur when one event does not have any relationship to the other, that it has no impact on the second event. And I also want to be sure that you understand the difference between independent and mutually exclusive, because they are very different concepts. Now, although you may talk to a roulette gambler, and the roulette gambler may say to you, the wheel is due to come up red. It's due for a red. In fact, there's an old saying that the wheel has no memory, that if, in fact, if it's come up red 5 or 6 times in a row, if it's a fair wheel, that it's not going to change anything. Unlike blackjack, where cards which have been dealt before do impact what's likely to happen in the future. The roulette wheel is not influenced by what's occurred before, if it's a fair wheel. Of course, the fact that blackjack as a gambling game, and I should mention to you that much of probability theory was derived by gambling interests in the 17th, 18th century, where gamblers would retain mathematicians to be able to help them stack the odds in their favor. Perhaps maybe today's not that much different. Oftentimes business people employ people who build simulations for them, or try to find some other ways of stacking the odds in their favor. But what often occurs in gambling is that people like to feel that there's some influence that they can have, whereas in fact, except for very few games, what happens in the past does not impact what happens going forward. The fact that I flip a coin 10 times in a row and it's heads does not change that on the 11th flip, the chance of it coming up heads is still 50-50. There's no impact on those previous 10 events have on the 11th event, because the coin flip is independent. Now, it turns out that people like to think that they can use conditional probability and to work for them very effectively. In fact, my son, maybe 2 years ago, said, "Dad, let's go to Las Vegas, because I have this card counting system which will for sure pay off." And I said, "Okay, I'll go over, we'll do a little gambling, I'll play a little bit of golf." When we got over there, it turns out that the minimum stakes it was Friday, Saturday, I think we had a deal where we'd get a room for free. And the minimum stakes were very high. I forget what they were, I think $10 per bet. Now, he was a college student, and I didn't necessarily want him, because even though if you stack the odds slightly in your favor based upon conditional probabilities, which are based upon the fact that you're counting cards, and that affects whether or not you're going to get a high card or low card on the next turn of the card, still, I did not want for him to, waste or gamble a lot of money, because you can get a bad streak even if the odds are slightly in your favor. So I said, "You go across the street." We had to gamble so many minutes in this hotel in order to get our room for free. So I said, "I'll handle this. I'll take care of the minimum number of hours that we have to gamble in this hotel. You go across the street and play on the $2 tables and try your system over there." So what I did is I did not go to the blackjack table. What I did is I went to the slot machine. Now, you say, why do you go to the slot machine? The odds are skewed against you, I would think, if you played slots. Yes, but here's what I did. I put a quarter in the slot, and I waited till it forced me to put another quarter in to play. Each time I played a quarter, I was getting 3 minutes, it turns out, of credit. So I figured this way, 3 minutes times 20 quarters an hour is the maximum that I have to put in, which means the maximum I can lose is $5 an hour. And I only have to gamble for 4 hours to get the room for free, so the maximum I can lose is $20 for the room. And I had papers to read anyhow. But what happened was I'm sitting there waiting 3 minutes, then put another quarter in, pull the slot handle, wait 3 minutes. What happens is that I start to win. Just by pure random chance, I start to win. So people are starting to look at me. What is this guy, got some system to wait 3 minutes and then pull his handle? And I almost, in my local area, caused a little slowdown as far as what was occurring. And I wound up by pure chance, which was stacked against me, to win something like $50 over the 4-hour period of time. But the maximum I could have lost was $20 based upon how I figured it out. So the point is this. Independent events occur when the event does not have any relationship to another. And again, the roulette wheel has no memory. The important thing for us to notice that if events are independent, if A and B are independent, then the probability of A and B is equal to the probability of A times the probability of B. So in an illustration I used in an earlier lecture, the chances of me making 10 free throws in a row, if my probability is 60%, I could take those 0.6, 0.6, 0.6, 0.6, and multiply them together, which came up with something like 6 chances in 1,000 or whatever, that I would be able to sink 10 free throws in a row. And the chances of 5 reds in a row in roulette is A and B and C and D and E, 18 38ths. There's 18 reds, 18 blacks, and 0 and double 0, times 18 38ths, times 18 38ths, times 18 38ths. Finally, one more. That gives me a probability of around 2%. There's a 2% chance that 5 reds will be rolled in a row. The reason I can multiply them together is that they are independent. I couldn't multiply them together, obviously, if there was some stacking of the wheel or weighting of the wheel. Now, let's talk about a financial example in financial markets. If financial markets are efficient, what we mean by efficient is that they quickly reflect all marketplace information, that all information that is known about a security is almost instantaneously reflected in the stock price for that security. So it moves quickly to respond to information. The two events, event A, the market went up today, and event B, the market went up yesterday. If those events, if the market is efficient, those events are independent. The events are independent because what happened yesterday should already be reflected in yesterday's prices. It shouldn't affect what happens today. That they're independent events, and one event does not have any relationship to the other. Now, you'll have debates about the efficiencies of the market, the relative efficiencies from academicians and people who practice in financial markets. But if they are efficient, the two events, the market went up yesterday, the market went up today, are independent events. Now, let me differentiate for you, because sometimes people get this confused, that there's a difference between events being independent and events being mutually exclusive. If two events are mutually exclusive, if they're mutually exclusive, if there is no overlap in their probability space, then almost certainly, and I'll say almost certainly, they are not independent. They're not independent because if this one happens, it affects whether or not this one happens. So if events are mutually exclusive, one event does have a relationship to the other. And consequently, they cannot be, the relationship is they both can occur. They both cannot occur, and consequently, they must be independent. They are not independent. Now, there's one exception to that, which is trivial. The probability of one can be equal to 0. But let's not worry too much about some of the subtlety. What I want to do in the final few minutes we have with this lecture is to check your understanding. Let me check your understanding with a problem. And again, I'm not going to call on the audience to be able to give me the answer to this problem, but let me set up this problem and see how you're doing in thinking about probability. And again, next time we'll deal with this question of simulation. And then we'll wind up the series of lectures on probability and simulation with a lecture on simulation. Then we're going to move on to statistical analysis and eventually to regression. Here's the problem. You apply for 4 jobs and have a 1/4 chance of getting each one. Assuming independence, what are the chances of getting at least one? Okay? So these are independent events, which is an assumption we're making, and you have a 1/4 chance of getting each one. What are the chances that you'll get at least one? Now, I give you some choices here. The first is, can I just add them up? 1/4 plus 1/4 plus 1/4 plus 1/4 equals 1. Can you do that? Can you add up the events and say that it's almost certain that I will get, it is certain that I'll get one offer? The answer is a big no. You can't add them up. And why can't you add them up? You can't add up those probabilities because they are not mutually exclusive. In other words, if this is my entire sample space, and here's A, B, C, and D, if they each occupied a distinct 1/4 of the sample space, I could add them up and get one. But it's possible that I could get more than one job offer. They are not mutually exclusive. So events that are not mutually exclusive, I simply can't add up because I have overlap in their sample space. So, in fact, you could say this way. Well, if that were the case, if I had 5 job offers, and a 1/4 with each one, and if they were independent, I could get 5/4, which doesn't make any sense because probabilities can only be equal to 1 as an upper limit. So I just cannot add them up. This is wrong, okay? Secondly, I can't multiply them. I can't multiply them together and say the answer is 1/256. Why not? Well, this is the probability of getting all 4 job offers, of getting everyone to offer me the job, right? It's not the chances of getting at least one. This is the chances of getting all 4. So you say, well, how do you solve a problem like this? Well, let me illustrate how to solve this one and then come up with the conclusion for our lecture. What you would have to do, the easiest way to solve a problem like this is to come in the back door. And what I mean by that is the probability of not getting a job offer of A is 3/4. The probability of not B is 3/4. Okay? Now, the probability of not A, not B, not C, and not D are independent, and the probability of getting 0 job offers will be 3/4 times 3/4 times 3/4 times 3/4, or 81/256. Now, one of 2 things has to happen. Either I'm going to get no job offers, or I'm going to get at least one. So these are mutually exclusive. The probability of greater than 0 is mutually exclusive with respect to the probability of getting 0 job offers. So this will be equal to 1 minus 81/256. And if you do the math, it comes out to be about 175/256. That's not about. This is about. And that turns out to be about 68%. So what that means is that there is about a 68% chance that I'll get one job offer, at least one. I may get more than one, but I'll get at least one job offer, 68% chance if I have 4 jobs. The probability of each of the jobs is 1/4, and they are independent events. So what do I want you to take away from this lecture? What I want you to take away is the following. Real world situations are complex. We started off by talking about simulation, which shows a little bit how we can start to deal with that complexity. We can deal with competitor entries. We can deal with the fact we don't know exactly what the revenues are going to be, but we can kind of describe how they're going to be probabilistically. What our cost structure is going to be probabilistically. We can model. And we can get a forecast for our revenues, which doesn't tell us exactly what they're going to be, but gives us not only a range, but the likelihood of falling within a certain segment of that range. So real-world situations are complex. Concepts such as conditional probability, of independence, and of simulation can help us handle that complexity.